Good morning, everyone. So, today's lecture number is 33 of this heat treatment class. And recently, if you remember in the previous lecture, we were in the new topic that is on carburizing. So, which means basically we have to increase the weight percentage of carbon on the case of the steel or on the surface of the steel, right? Because you understand a lot of failure starts from the surface itself, right? Because surface is always exposed to the stress, basically, right? Like fatigue failure. Fatigue failure starts from the surface of the steel, right? So you can increase the fatigue strength by increasing the strength of the surface of the steel, or hardness of the surface can be increased, and you can increase the fatigue life of the steel. Similarly, wear also starts from the surface of the steel, right? So you can prevent the wear if you make the surface harder. So one of the the best way is you can carburize the surface of the steel, right? By increasing the weight percentage of carbon on the surface of the steel, right? Because you understand, more is the weight percentage of carbon, more is the hardness of the steel, right? So, and also in the previous lecture, we have discussed about the types of carburizing. That is solid carburizing, liquid carburizing, and gas carburizing. Solid carburizing is also called PEG carburizing, and other carburizing, liquid and gas. And the difference between them is what? The medium we are using as a carburizing medium, or the carbonaceous material which we are using to make the sample carburized, right? So, now already we have discussed about the solid carburizing, liquid carburizing. Now the next carburizing process is the gas carburizing process, which is the most usually used process, basically. Because it is somewhat faster. The gases can diffuse at a higher rate compared to that of the liquid and compared to that of the solids. Right? And today's another topic is we'll discuss about the post carburizing objective. We'll not go into the depth of this topic, but here we'll discuss about the objective of that, and or why we need to do post carburizing. But if you look carefully, finally we can have a heat treatment cycle which we don't want any kind of post carburizing heat treatment. We'll do just carburizing, but it will be a kind of cyclic heat treatment. We'll go in a cycle way, so that we can have very high case hardness, and we can have a refined grain also at the core, right? So simultaneously, you understand, this kind of heat treatment cycle will give you very high hardness of the surface of the steel, uh, plus good toughness of the core, right? Because if you remember the earlier lecture, in many cases where we need a high wear resistance surface and a good toughness core, core with good toughness or good ductility. So gas carburizing. So this is the most widely used process. As I told, it is a very fast process compared to liquid and solid. So this is the most widely used process. And second, if you look into the temperature of carburizing, it is 870 to 950, like liquid carburizing temperature. Here, but one thing here, just look at the carburizing atmosphere. Here you can use both liquid and gases, hydrocarbons. These are basically hydrocarbons, right? So propane and methane, or you can use methanol or isopropanol as a carburizing medium. These two are liquid carburizing medium. These are gases carburizing medium. These are hydrocarbons. Then you can see the main carburizing takes place here due to conversion of carbon monoxide to carbon dioxide. So you can see the reactions which happens during the gas carburizing. These are the reactions which happen during the gas carburizing. You can see C3H8 undergo cracking to give you methane plus carbon, and this methane react with iron to leads to the carburizing of the iron and give you hydrogen gas. This is not the main reaction, but still this reaction will go on. Then methane also react with carbon dioxide to give you 2 carbon monoxide plus hydrogen. And finally, this carbon monoxide react to the surface of the steel, or that is iron, give rise to carburizing of the iron surface. This bracket carbon means the steel surface will enrich with the carbon, right, plus CO2. Then finally, another kind of reaction may happen, like hydrogen plus carbon dioxide gives rise to carbon monoxide plus water. So these are all the reactions happen, and this is the most important reaction: carbon monoxide becoming carbon dioxide, and which enrich the steel surface with carbon. And this is very nice figure you can see. Can you people figure it out? What is it showing? I'll give you 2 minutes to have a careful look at this picture and tell me what difference you are getting, or can you figure it out what is happening here? Just carefully look at the picture and tell me.
So more carbons are on the case region.
Okay, fine. Anything else you can figure it out?
So smaller the crack in case region.
It is not a crack actually. Well, you people have seen a indentation mark. Have you ever seen an indentation mark while measuring a hardness?
Yes, sir.
Okay, so that is the indentation mark. Now, can you figure it out?
So the size of indentation is more in core.
More in core and less in
Yes.
case. Very good. So that is the main thing. So Amiz have identified that one. Very nice. So you can see the indentation mark is here and indentation mark is here. So that means uh, after doing carburizing, so this is a specimen, and this is up to here, this is the core, which is now enriched with the carbon, black portions, darker portions, and this is the core part of the steel from here to here, right? So after enriching the surface of the case with carbon, we have taken hardness value. We have do indentation to find out the hardness. So this is the indentation mark in case of case. This is the indentation mark in case of core, and you can see the difference. Here the indentation is very prominent, but here the indentation is not so prominent. So indentation is prominent means uh, more plastic deformation has happened here. Okay, the less plastic deformation has happened here. So more plastic deformation has happened here means the resistance to plastic deformation is less here, but resistance to plastic deformation is more here. So that means this part is softer, this part is harder. Why harder? Due to more carbon concentration in the case resin. So this is one of the very good figure you can see. Okay, so now these are the difference between this pack carburizing, this solid carburizing, liquid carburizing, and gas carburizing. So you can have a look. The major difference between them is you should understand the carburizing medium is different: solid, liquid, and gas. But in gas, we can use both liquid and gaseous medium, hydrocarbons. And gaseous carburizing is a very fast process. Here already written production rate is high here. And component, if you look into the small components, symmetrically sized shape components, this is also for small components, and this is for any size components. And this is very time consuming process. This is a very fast process. This is intermediate. Okay. Now, post carburizing heat treatment. So should understand, post carburizing heat treatment means, that means we have to give another heat treatment just after carburizing heat treatment, right? So you might have a question, why again we have to do a post heat treatment after carburizing? Because after carburizing, finally we'll get a steel having more concentration of carbon at the surface, right? So our aim is fulfilled, our objective is done. But what might be this problem you think of it? Can anybody think of this, why a post carburizing heat treatment is needed? The hint I can give you is, this carburizing heat treatment, you can see the time. Suppose you are doing solid carburizing, you can see the solid carburizing time is 7 to 8 hours. So can you think of it, why a post carburizing heat treatment is required? If the time duration of carburizing is this much, why we need a post carburizing heat treatment? That comes from this one, time duration. And temperature also, you can see the temperature is suppose 1000 degree or 970 degree.
सर ब्रिटल हो जाए पारे हमको टफनेस अधिक दरकार मटेरियल रे
Okay.
सर कोर रे भी जदी कार्बन कंसंट्रेशन बहुत बढ़ जिवो तो ब्रिटल हो जो मटेरियल टा जदी
Okay,
अधिक
fine.
टाइम रे डिफ्यूजन हो
Uh, anything else? Anybody want to say anything else apart from this? Again, I am saying the time and temperature. The temperature is high, time period is also. Sivasis has figured out something, but you can see Sivasis. The thing is what? Just look at the depth. Okay, so this one is liquid, solid one. Okay, depth one is up to 2 mm only. Okay, this one, yes. You can see if the time duration is only 7 to 8 hours, the case depth is 2 to 3 mm only. That means up to 2 mm depth, the carbon enrichment will be taking place, not up to 5 mm, 6 mm. You can control the time also, and temperature is high. Okay, how many of you remember what happens at high temperature basically? If you
ग्रेन कोर्सनिंग
grain coarsening, very good. That is the answer. Grain coarsening will take place because the temperature is very high, and if the duration is also high, like in case of carburizing, the grain will become coarser. Right? So we want a steel which should have high UVA resistance and high toughness. But in one end, we are improving the weight percentage of carbon onto the surface, which will increase the UVA resistance of the steel. But in another end, the grain will become coarser at the core also. So core will become more ductile. It will not become tougher, because toughness can be obtained if the grain size will be finer. Right? So due to the answer is what? Due to high temperature and more exposure time, the grain become coarser. So the toughness cannot be maintained at the core. It will become more ductile. Okay. So you can write why post carburizing is needed. Due to grain coarsening, toughness of the core reduces. Right? That is one part. Another part is, can anybody think of this? Anything else? Suppose after carburizing, you are doing annealing. or you are just doing, yeah, suppose you are doing annealing, you're cooling the thing in furnace, what will happen? That is related to the carbon concentration.
Carbide formation.
Yes, very good. Carbide formation, but which kind of carbides?
Some stable carbides like
Stable
niobium, vanadium.
carbides, no. Suppose it is a plain carbon steel. Then, if you remember, we basically choose carburizing heat treatment for plain carbon steels. Alloy steel is very rarely chosen, but sometimes we choose. But basically, we prefer low carbon steel because low carbon steel have good toughness. We have to increase the hardness of or wear resistance of the case only, the surface only. Network of carbides may form. You understand? If the concentration of carbon will be so high, like near to the 1 weight percentage, sometimes network of carbides form. And network carbides are good or bad for the steel property?
Bed.
Yes. Why they are bad? Or why they are
Crack
deleterious?
propagation is easier.
Class crack
Crack
propagation will be
propagation.
easier. Why? Because networks of carbides are there. Carbides are basically brittle in nature. If a crack will initiate, that will find a easy path for its propagation. So that may be the another reason of giving post carburizing heat treatment. This is not always true, but sometimes when the carbon content is very high, formation of what? Network of carbides. Formation of network of carbides. That may be the another reason. Condition, concentration, of carbon is too high. Too high. Right. So now what is the objective of post carburizing? So main objective of post carburizing is, obviously you should understand, to refine the grain so as to get good toughness at core, high hardness at case, and to break carbide networks So these are the main objectives. But we will not discuss about the post carburizing. You can go through the textbook, what we basically do in the post carburizing heat treatment. But since I am not discussing because it's not so important, but still you can go through that. But we instead of doing so much of thing, like we will do carburizing, then we'll do post carburizing, better we should find a way so that we can achieve good toughness at the core and we can achieve high hardness or wear resistance at the surface or at the case, right? So there is a method. So that is called recommended heat treatment cycle for maximum case hardness along with grain refinement. So what is that heat treatment cycle? That consists of 4 heat treatment cycles. 4 heat treatment cycles it consists of. So first is what? So the steel specimen will be heated to a very high temperature. Then it will be like the steel is heated to a temperature of 1040 degrees centigrade in the carbon atmosphere or carburizing atmosphere. Then it will be done oil bath quenching. Oil bath quenching. Oil bath quenching, you understand, because no cracks will form if oil bath quenching will be taking place. Then again, next heat treatment cycle is tempering. But this tempering is done at high temperature, like 370 degrees centigrade. Why? To convert any written austenite into bainite microstructure. So you should remember this one. This is important. Why tempering is done? Here the tempering main objective is to convert any written austenite into bainite. Fine. Then the next heat treatment cycle is, again you do austenitizing of this steel by induction heating, because induction heating means very fast heating rate. or up to a very less depth of heating will be taking place. So next, you can see, but here the austenitization will be done at a low temperature compared to that of initial temperature. Suppose this is 1040, this will be below 1040. Then again it will be oil quenched. But you have to remember the third heat treatment cycle, which is austenitizing at low temperature, this will be done at a very fast rate. Very short period of time will be given. And last one is again tempering. But this kind of tempering is done at low temperature. You can see the second tempering is done at 370, where this tempering is done at like 180 or 150, 160, like that. So these are the 4 heat treatment cycles to be done to a steel to obtain high case hardness and finer grain size of the core. So our objective will be fulfilled. So conclusion is, you can see austenitizing at very high temperature for short time and oil quenching, then tempering at high temperature, then austenitizing for short time at high temperature and oil quenching. This is very high temperature I have written, and this is high temperature only. And finally is the tempering at low temperature. So this is the preferred heat treatment cycle for carburizing also, you can see. So you can see for alloy steel, suppose you want to do carburizing of low alloy steels. So there might be some problem. Sometimes because alloy steels means, you understand, the MS and MS temperature go down.
Sir, last slide रे जो टेम्परिंग वाला था सर सेटा टिके ड्रॉ करिकि ता साइकल टा देखे परिबे कि?
Okay, sorry, actually, okay, let me show you the video. Yes. Okay, just look at the video. This one. Is it visible?
Yes sir.
You can see the first stage one is carburizing at a high temperature, then oil quenching. Right? The duration is somewhat higher. Then just after oil quenching, you have to do tempering. But this tempering is done at high temperature. Right? Our main objective is to convert our written austenite into benite. Then again you have to do austenitizing at high temperature, but it is not so high like in the first stage, the first step. Then but this time period is very small. Then again you have to do oil quenching of that. And finally we have to do again tempering, that is at low temperature. So tempering is essential, you understand. Quenching is done, so tempering is essential. Okay, I think it is fine. So what is
Sir CCT curve रे टिके.
CCT curve? Okay, CCT curve. Right now I cannot draw it. I'll show you later otherwise.
Okay sir.
Right now I don't have the pen and all those things, so I cannot draw it. Okay, do you have any issue with this CCT diagrams, like how microstructure will evolve? If you want, I can take another class of that, CCT or TTT. How microstructure is getting evolved, or which kind of microstructure you will get upon different cooling rates. You want that?
ना सर टेम्परिंग करिकि सर बेनाइट केमते फॉर्म कला बिकॉज़ टेम्परिंग में मार्टिन साइड
Tempering. Okay, fine. Just go through this one. Otherwise, okay, let me show you. Okay, do you remember what happens when you quench the steel? Which kind of microstructure will obtain?
मार्टिन साइड.
Basically martensite, but since it is a oil quenching, you may not get 100% martensite. It depends. No? But that means when martensite will form, what happened to the carbon? What happens to the carbon when martensite forms? Can anybody answer? What happens to the carbon when we do quenching?
Sir, it is present in the voids.
It is present in the voids. When okay, in austenite, it is not present in the void.
Yes, sir, in voids also.
Yes. So what happened to the carbon when we do quenching? That means the carbon do not find any time to escape out, right? It form a martensitic structure. Martensitic structure means what? A lot of carbon is there. It is a saturated. Sometimes we call martensite as a saturated microstructure. It is saturated with or supersaturated solid solution, you can say, because it contains a lot of carbon in it. The carbon cannot escape out because of high rate of cooling. So when this martensite will heated again, so what will happen?
The carbon will come out of the voids.
Carbon will eject out, right? Very good. If you remember the tempering process. So what happens? Sometimes it may lead to formation of epsilon carbide also.
Yes, sir.
It can form some intermediate carbides. Let me tempering of okay, let me find it out. Effect of following element on tempering. Okay. Let me check. You can see what is written over here. Upon tempering first non-equilibrium carbides, non-equilibrium carbide forms like eta or epsilon carbides. Which are small in size. This carbide range this composition is Fe2C to Fe2.4C.
Sir, allow me to join.
Suppose this one, you look at this one. If you're heating the steel again and you are holding the steel at this temperature for certain period of time, so the martensite, the written austenite, suppose, listen carefully. Sivasis, you are there?
Yes, sir.
Just look at this one. Look at this one. Suppose you do quenching, you do oil quenching. Upon oil quenching, what is happening? The austenite will be transformed into martensite. Yes or no?
Yes, sir.
Right? But since it is a oil quenching, sometimes what happens? Some written austenite will be still there. Yes or no?
Yes, sir.
Right? So again, you are hitting. Suppose this is the temperature. You have martensite and written austenite. Again, you are rising the temperature and you are holding at this temperature, for example. And this temperature range is which temperature range?
Benignitic.
Benignitic temperature range. So chances is what? And written austenite is there. So
they will
austenite may transform into benign. If this is the temperature range, yes or no?
Yes, sir.
You understood now?
Yes, sir.
Okay, fine. So that's why I told it is a high temperature tempering. The second stage is high temperature tempering. What is the temperature? Above 300. You can see. And that is the benignitic temperature range. 370 or 360, what I told.
Yes, sir. 370.
370.
Lower benign.
370 degree temperature is the benignitic temperature range. So the written austenite is there. So transformation starts from austenite to benign at that temperature. It is okay.
Yes, sir.
So now, so this is the thing. So and the problem you can see, suppose we are dealing with some alloy steels and we are doing this four heat treatment cycle to get high case hardness and high toughness core, that is refined grain. So we can end up with this problem. What is the issue? The main issue is we can have a reduced hardness. Why? Due to formation of written austenite. Because MS and MF temperature go down, so we can have a written austenite, and written austenite is soft phase. So in that case, we have a solution. We can do austenitization, then we can go for sub-zero treatment. This is basically for alloy steels, but this is basically for your carbon steels. Right? So I'll end the topic here. We'll continue our discussion in the next class.